Hello students, welcome to EPG Pathshala. I am Dr. Vikas Jain from BS Anangpuria Institute of Pharmacy, Faridabad. Today we are going to discuss about the module Emulsion Part 2 under Paper Product Development. The learning objects of this particular module is emulsion formation process, formulation consideration, stability consideration, product development with illustrative examples, evaluation and testing. Oral emulsion, oral emulsions are almost exclusively of oil in water type. They provide a degree of taste masking as the aqueous external phase effectively isolates the oil from the tongue. Mineral and castor oils have been emulsified in water and administered orally for the local treatment of constipation for many years, as have various nutritional oils from fish liver or vegetable origin to produce oral liquid food supplements. It has long been established that the use of oil in water emulsions as carriers for lipophilic drugs may improve oral bioavailability and efficacy. For example, graciofulvin formulated as an oil in water emulsion has enhanced gastrointestinal absorption when compared with suspension, tablets or capsules dosage form. An emulsion is a thermodynamically unstable system consisting of at least two immiscible liquid phases, one of which is dispersed as globules throughout the dispersion medium, stabilized by the presence of an emulsifying agent. In an oil and water emulsion, oil globules are dispersed in aqueous phase. The reverse is true for water in oil emulsion. The diameter of dispersed phase globules generally in the range of 0.1 to 10 micron, though some as small as 0.01 micron and as large as 100 micron are not uncommon. Heterogeneous system comprising emulsions offer greater difficulties in manufacturing, where not only a careful calculation of formulation additives such as surfactants is required, but also the manufacturing techniques such as mixing time, intensity of mixing and temperature become critical. Microemulsion manufacturing requires special equipment, and recently the use of nanoparticles has created a need for highly specialized handling systems. Homogenizers are used to emulsify liquids along with ultrasonifiers and colloid mills. In some instances, spontaneous emulsification is obtained by a careful order of mixing. The choice of emulsifying agent depends on the type of emulsion desired and determined by the use of hydrophilic lipophilic balance. The temperature at which emulsion is formed can often affect the particle size and thus the tendency to coalesce or break. Auxiliary emulsification aids include use of fine solids. Hydrophilic colloids are commonly used to impart proper viscosity that enhances stability of emulsions. However, there is a tendency to build up viscosity with time in freshly prepared emulsions. The flow characteristics of emulsions are important and are determined by the emulsion's yield value. Consistency in the density character of emulsion is therefore important. Clear emulsions have a lower proportion of internal phase and require solubilization techniques and more frequently than do opaque emulsions. Scaling up of emulsion formulation from laboratory to manufacturing scale often presents significant problems related to temperature distribution studies. Often the two phases are mixed at a specific temperature that may change during the mixing process and thus require a certain mixing rate. Stability testing of emulsions is subject to protocols different from those used for other liquid products. We'll put an emphasis on emulsion formation process. The spontaneous formation of an emulsion is a rare occurrence. Emulsion preparation by dispersion method requires breaking up the internal phase into droplets and for stabilizing them in the external phase. Usually, the breakup of the internal phase by physical means is fairly rapid. The stabilization step and the rate of coalescence are time and temperature dependent processes. The application of energy is required to reduce the internal phase into small droplets. Thus, scheduling of work input becomes another important physical parameter. Condensation method. Vaporization is an effective way of breaking almost all the bonds between the molecules of a liquid. It is possible, therefore, to prepare emulsions by passing the vapor of a liquid into an external phase that contains suitable emulsifying agents. This process of emulsification, called the condensation method, is relatively slow, is limited to the preparation of dilute emulsions of materials having a relatively low vapor pressure, and is therefore primarily of theoretical importance. Phase inversion method. The temperature at which the inversion occurs depends on the emulsifier concentration and is called phase inversion temperature. This type of inversion can occur during the formation of emulsions since they are generally prepared at relatively high temperatures and are then allowed to cool to room temperature. Emulsions formed by a phase inversion technique are generally considered quite stable and are believed to contain finely dispersed internal phase. The phase inversion temperature is generally considered to be the temperature at which the hydrophilic and lipophilic properties of the emulsifier are in balance and is therefore are also called the HLB temperatures. We will now discuss low energy emulsification process. In low energy emulsification, all of the internal phase but only a portion of the external phase is heated. After emulsification of the heated portions, the remainder of the external phase is added to the emulsion concentrate, or the preformed concentrate is blended into the continuous phase. In those emulsions in which a phase inversion temperature exists, the emulsion concentrate is preferably prepared above the phase inversion temperature, which results in emulsions having extremely small droplet size. As in the case of classic emulsification technique, the temperature for the preparation of the emulsion concentrate is critical. It is important to effect in situ neutralization of acidic emulsifying components during the emulsion step. Almost all methods used for breaking up the internal phase into droplets depend on the brute force and require some sort of agitation. When a liquid jet of one liquid is introduced under pressure into a second liquid, the initially cylindric jet stream is broken up into droplets. The factors that enter into the breakup of liquid jet include the diameter of the nozzle, the speed with which the liquid is injected, the density and the viscosity of the injected liquid, and of course the interfacial tension between the two liquids. A similar breakup into droplets occurs when a liquid is allowed to flow into a second liquid that is agitated vigorously. Once the initial breakup into droplets has occurred, the droplets continue to be subject to additional forces due to turbulence, which causes deformation of the droplet and further breakdown into smaller droplets. Various types of equipments are available to affect droplet breakup and emulsification either in the laboratory or in production. We will now have a glimpse of various mechanical equipments used for emulsification. The first part is mechanical stirrers. An emulsion may be stirred by means of various impellers mounted on shafts, which are placed directly into the system to be emulsified. Simple top entering popular mixers are available for low viscosity emulsions. Turbine type mixers are available for moderate viscosity emulsions. Other mixers provided with paddle blades, counter rotating blades, or planetary action blades are available for special requirements. Another equipment is homogenizers. The dispersion achieved by forcing mixture through a small inlet orifice at high pressures. Homogenization raises the temperature of the emulsion and subsequent cooling may be required. It provides reasonably monodisperse emulsion of low particle size, and examples of this particular equipment include high shear and high pressure homogenizers. Next category is ultrasonifiers. This equipment is based on the use of ultrasonic energy. It has limited output and are relatively expensive. It is useful in the preparation of emulsion of moderate viscosity and extremely low particle size. The last category is colloid mills. Colloid mills operate on the principle of high shear generated between the rotor and the stator of the mill. It is useful for the preparation of relatively viscous emulsions. An emulsion that is generated without the application of any external agitation is known as spontaneous emulsification. Examples of spontaneous emulsification do include emulsifiable concentrates and microemulsions. The phenomenon of spontaneous emulsification is observable when a drop of oil is placed on an aqueous solution of an emulsifier, in which case the interface becomes extremely unstable and results in the formation of fine droplets. Spontaneous emulsification evidently is not practiced commercially. In general, the considerations applicable to opaque emulsion are also pertinent to the preparation of clear emulsions. The amount of interface in clear emulsions or in solubilized systems is generally lower than that in opaque emulsions. Most emulsion technologists have found that an increase in the surfactant concentration reduces the opacity of all types of emulsions and, if carried further, can result in solubilization. Cosmetic and pharmaceutical microemulsions usually do not employ the co-solvents required for more classic microemulsions of theoretic interest. Instead, modern commercial solubilized systems are frequently based on non-ionic emulsifiers, which results in the formation of micellar solutions. The actual location of the drug is described by a micellar distribution coefficient as defined Km equals to Sm divided by Sw. Sm is the solubility of active ingredient in micellar phase and Sw is its solubility in water. The value of Km is established by classic solubility determinations. Production aspects of emulsion are discussed in this particular slide. The first parameter under discussion is foaming during agitation. During the agitation or transfer of an emulsion, foam may be generated. Foaming occurs because the water-soluble surfactant required for emulsification generally also reduces the surface tension at the air-water interface. To minimize foaming, emulsifications may be carried out in closed apparatus and under vacuum also. In addition, mechanical stirring, particularly during the cooling of a freshly prepared emulsion, can be regulated to cause air to rise to the top. If these precautions should fail to eliminate or reduce foaming, it is sometimes necessary to add foam depressants or antifoams. However, their use should be avoided, if at all possible, since they represent a chemical source of incompatibility. Chemical inertness is an absolute and almost obvious requirement for emulsion ingredients. For example, it would be futile to utilize soap as an emulsifier in a system having a final pH of less than 5. Similarly, one would not use an easily hydrolyzed ester in an emulsion that is either acidic or alkaline. Some lipids are subject to chemical changes due to oxidation, that is rancidity. In general, it is simpler to avoid their use than to depend on antioxidants to ensure their stability. Unfortunately, predictions of hydrolytic stability made by classic chemical or pharmaceutical procedures may on occasion be unreliable as a result of micellar catalysis. Safety and toxicologic clearance of components of pharmaceutical and cosmetic emulsions are absolute requirements. It is essential, therefore, for the formulator to depend heavily on toxicologic information from suppliers or in the scientific literature, as well as on regulatory activities by governmental agencies. Despite these almost obvious limitations, the formulator has an enormous choice of emulsion ingredients which differ in their cost and their ability to yield the desired product. In the preparation of anionic or cationic oil in water type emulsions, it is customary to add the oil phase to the water phase, although some technologies prefer the inversion technique. In the case of non-ionic emulsions, which exhibit a phase inversion temperature, the inversion technique is not required since temperature alone can be used to control this stage of emulsification. If soap is used as the emulsifier, it is usually prepared in situ. Oil-soluble emulsifiers are commonly added to the lipidic phase, where water-solubles are added in aqueous phase. In the preparation of water in oil-type emulsion, it is almost always necessary to add the water phase slowly to the oil/emulsifier blend. To avoid losses, volatile flavors and perfumes are preferably added at the lowest temperature. If a gum is employed, it should be completely hydrated or dissolved in aqueous phase. It is also noted that anionic and cationic emulsifiers in about equimolar quantities rarely yield satisfactory emulsion. Emulsion designated for parenteral administration can be prepared with a limited number of emulsifier that has been discussed separately. It is recommended in case of parenteral emulsion, especially designed for intravenous injection, it should be homogenized until a satisfactory particle size is achieved. Since use of conventional preservatives is contraindicated, such preparations require sterilization at high temperature but must still yield acceptable emulsion. Whenever an emulsion is formed at elevated temperature, the loss of water due to evaporation must be made up. This is done best by adjusting the final weight with water when the emulsion reaches at a temperature of about 35 degrees centigrade. We will now discuss the preparation of oil and water type oral emulsion. The composition is cottonseed oil 460 grams, sulfadiazine 200 grams, sorbitol monostearate 84 grams. The second portion comprises of polyoxyethylene 20 sorbitol monostearate 36 gram, sodium benzoate 2 grams, sweetener quantity sufficient, and potable water up to 1000 gram, and flavor oil in a sufficient quantity. This emulsion is to be prepared by the given procedure. The first part, heat portion A to 50 degrees centigrade and pass through colloid mill. Second step, add portion A at 50 degrees centigrade to portion B at 65 degrees centigrade and stir while cooling to 45 degrees centigrade. Add component C and continue to stir until room temperature is reached. In this preparation, sulfadiazine is essentially water insoluble. A suspension or emulsion is required to yield a fluid oral dosage form. To maintain sulfadiazine in suspension, the viscosity of the final product must be reasonably high. This could be achieved by the use of gums or by developing an emulsion high in internal phase. The choice of cottonseed oil and water emulsion is probably arbitrary except for the fact that oil and water preparations are quite palatable. From the knowledge gained till this point, we know that HLV value of about 10 is required to yield a fluid emulsion of cottonseed oil, although a single emulsion and flavor oil in a sufficient quantity. This emulsion is to be prepared by the given procedure. The first part, heat portion A to 50 degrees centigrade and pass through colloid mill. Second step, add portion A at 50 degrees centigrade to portion B at 65 degrees centigrade and stir while cooling to 45 degrees centigrade. Add component C and continue to stir until room temperature is reached. In this preparation, sulfadiazine is essentially water insoluble. A suspension or emulsion is required to yield a fluid oral dosage form. To maintain sulfadiazine in suspension, the viscosity of the final product must be reasonably high. This could be achieved by the use of gums or by developing an emulsion high in internal phase. The choice of cottonseed oil, oil in water emulsion is probably arbitrary except for the fact that oil in water preparations are quite palatable. From the knowledge gained till this point, we know that HLV value of about 10 is required to yield a fluid emulsion of cottonseed oil. Although a single emulsifier such as polyoxyethylene 4-sorbitol monostearate with an HLV value of 9.6 might be satisfactory, the use of mixed emulsifiers is generally preferred. In view of their safety and availability, a blend of sorbitol monostearate with HLV value of 4.7 and polyoxyethylene 20-sorbitol monostearate HLV 14.9 seems promising. It is found that a blend of 48% of lipophilic and 52% of hydrophilic emulsifier yields the desired HLV. In fact, the formula calls for a 70% of the hydrophobic emulsifier equivalent to an HLV of the blend of 8.2. This must be attributed to the presence of sulfadiazine and the need for a high viscosity emulsion. The ratio of emulsifier is to oil, that is about 1:4, is high and again points toward an unpredictable effect of the sulfadiazine. We will now discuss the preparation of high internal phase water in oil type emulsion. In this, two portions has been created. The first portion comprises of glyceryl monoisostearate at 2.5 weight by weight, isoparaffin 5% weight by weight, mineral oil 5% weight by weight, microcrystalline wax 0.3% weight by weight, acetylated lanolin 1% weight by weight, propyl para-hydroxybenzoate 0.1% weight by weight. The second portion comprises of monosodium glutamate 3%, methyl para-hydroxybenzoate 0.2%, water 82.7% weight by weight, and perfume 0.2% weight by weight. In order to prepare the emulsion, the procedure that has to be followed include heating of portion A and B separately to about 60 degrees centigrade, adding the aqueous phase to the oily phase and homogenize. At last, perfume is to be added at about 40 to 45 degrees centigrade. This low viscosity skin cream illustrates the concept that exceptionally high internal phase ratio products can exhibit reasonable stability. Glyceryl monoisostearate probably has an HLV of about 3.5 to 4 and is a good water in oil emulsifier. The key to the stability of this preparation is the use of an amino acid salt as an emulsion stabilizer. The practical feasibility of this approach is documented in European Patent 9404 of 4th February 80, but no theoretic basis for this concept has been provided. Becher has indicated that physical properties of an emulsion and its stability cannot be considered separately. Accordingly, this section is concerned with more important physical properties of emulsions, their changes under external influence, and their relationship to emulsion stability. It has already been noted that on purely thermodynamic grounds, emulsions are physically unstable. A reduction of the interfacial area by coalescence reduces the system's energy, and this process is thermodynamically favored. For this reason, Garrett defined a stable emulsion as one that would maintain the same number of sizes of particles of the dispersed phase per unit volume of weight of the continuous phase. The total interfacial energy must be invariant with time to conform to this definition. Thermodynamic stability of emulsions differs from stability as defined by the formulator or the consumer on the basis of entirely subjective judgment. Acceptable stability in a pharmaceutical dosage form does not require thermodynamic stability. If an emulsion creams up, rises, or creams down, it may still be pharmaceutically acceptable as long as it can be reconstituted by a modest amount of shaking. Similar considerations apply to cosmetic emulsions. However, in the latter, creaming is usually unacceptable because any unsightly separation makes the product cosmetically inelegant. It is important, therefore, to remember that the standard of stability depends to a large extent on the observer, since subjective observations or opinions by themselves do not suffice to define such a parameter as acceptable stability. Stability should be defined in the sense given to it by Garrett, that is, on a purely objective basis. Shelf life is a useful term to describe the subjective evaluation of stability. A product's shelf life may be directly related to its kinetic stability, and kinetic stability means that physicochemical properties of an emulsion do not change appreciably during a reasonable long period of time. On the other hand, thermodynamic stability of the type commonly postulated for solubilized systems or microemulsions is generally temperature dependent. Thus, after the temperature of a solubilized product has been disturbed, it will eventually return to its original state when the temperature is returned to normal. Thermodynamics does not and cannot predict how quickly the original state is restored. As soon as an emulsion has been prepared, time and temperature dependent processes occur to effect its separation. During storage, an emulsion's instability is evidenced by creaming, reversible aggregation, that is known as flocculation, and irreversible aggregation, that is known as coalescence. Flocculation of the dispersed phase may take place before, during, or after creaming. It is best described as reversible aggregation of droplets of the internal phase in the form of three-dimensional clusters. Flocculation is influenced by the charges on the surface of the emulsified globules. In the absence of a protective mechanical barrier at the interface. For example, if an insufficient amount of emulsifier is present, emulsion droplets aggregate and coalesce rapidly. Flocculation of emulsion droplets can occur only when the mechanical or electrical barrier is sufficient to prevent droplet coalescence. In other words, flocculation differs from coalescence primarily by the fact that the interfacial film and the individual droplets remain intact. The reversibility of this type of aggregation depends on the strength of interaction between particles, as determined by the chemical nature of the emulsifier, the phase volume ratio, and the concentration of dissolved substances, especially electrolytes and ionic emulsifiers. A high internal phase volume, that is tight packing of dispersed phase, tends to promote flocculation. Thus, it is probably safe to say that most practical oil in water and water in oil emulsion systems exists in a flocculated state. Flocculation, emulsion, viscosity, and shear thinning may be closely related. The viscosity of an emulsion depends to a large extent on flocculation, which restricts the movement of particles and can produce a fairly rigid network. Agitation of an emulsion breaks the particle-particle interactions with a resulting drop of viscosity that is known as shear thinning. The second symptom of instability is creaming. Under the influence of gravity, suspended particles or droplets tend to rise or sediment depending on the differences in specific gravities between the phases. If creaming takes place without any aggregation, the emulsion can be reconstituted by shaking or mixing. The Stokes equation is most useful in gaining an understanding of the processes of creaming. In fact, creaming involves the movement of a number of heterodispersed droplets, and their movements interfere with each other and may cause droplet deformation. If flocculation takes place, the criterion of sphericity is lost, and complex interaction for these variations must be made before Stokes' law can be applied quantitatively to the behavior of emulsions. Despite its defects, Stokes' equation is qualitatively applicable to emulsion. It shows that rate of creaming is a function of square of radius of the droplet, that is, larger particles cream more rapidly than smaller ones. The reverse is also true, that is, smaller particles are less likely to cream. Stokes' equation also predicts that no creaming is possible if the specific gravity of two phases are equal. Finally, Stokes' law shows that the rate of creaming is inversely proportional to the viscosity, and this is the reason for the well-known fact that increased viscosity of external phase is associated with improved shelf-life. The third symptom of instability is coalescence. Coalescence is a growth process during which the emulsified particles join to form larger particles. Any evidence for the formation of larger droplets by merger of smaller droplets suggests that the emulsion will eventually separate completely or break. The major factor which prevents coalescence in flocculated and unflocculated emulsions is the mechanical strength of the interfacial barrier. This is particularly true in oil and water type systems containing non-ionic surfactants and in water in oil type emulsion systems in which electrical effects are negligible. Thus, it is widely recognized that good shelf life and absence of coalescence can be achieved by the formation of a thick interfacial film from macromolecules or from particulate solids. This is the reason a variety of natural gums and proteins are useful as auxiliary emulsifiers when used at low levels, but can even be used as primary emulsifiers at higher concentrations. Figure represented in the slide suggests the symptoms of instability problem of emulsion. A emulsion can be converted into a flocculated stage from where it can result in upward creaming or downward creaming. The emulsion can be inverted and phase inversion can take place. The coalescence, that is merging of droplets, can also take place that can further result in breaking. So these all are various instability phenomena associated with emulsions. The final acceptance of an emulsion depends on stability, appearance, functionality of the packaged product. The most obvious problems facing the formulator are: what is acceptable emulsion shelf life? What are the predictive indicators of shelf life? The formulator requires unequivocal and quantitative answers to these questions. As is true with most dosage form, the container used for packaging an emulsion may be expected to be a source of incompatibility. Possible problems include interaction of ingredients with the container, extraction of material from the container, and loss of water and volatile ingredients through the container or the closure. For this reason, whatever the nature of container, final evaluation of the product must be conducted in the container that will be used commercially. No quick and sensitive methods for determining potential instability in an emulsion are available to the formulator. Instead, he is forced to wait for interminable periods at ambient condition before signs of poor shelf life become clearly apparent in an emulsion. To speed up his stability program, the formulator commonly places the emulsion under some sort of stress. Alternatively, he may seek a test or parameter that is more sensitive for detection of instability than mere macroscopic observation. Both approaches may be faulty. Stress conditions normally employed for evaluating the stability of emulsions include aging and temperature, centrifugation, and agitation. These are three conditions on which emulsion shelf life can be tested. In this discussion, pertaining to stress conditions related to aging and temperature, it is routine to determine the shelf life of all types of preparation by storing them for varying periods of time at temperatures that are higher than those normally encountered. The Arrhenius equation, which predicts that a 10 degree centigrade increase in the temperature doubles the rate of most chemical reaction, is not applicable to emulsions. The Arrhenius equation is based on the concept that same chemical reactions take place at all temperatures, albeit at different rates. It is generally recognized that in case of emulsions, changes in temperature bring into play new reactions. It is important, therefore, for the formulator to realize that exposure to unrealistically high temperatures may produce meaningless results. It is clearly established that many emulsions may be perfectly stable at 40 or 45 degrees centigrade but cannot tolerate temperature in excess of 55 or 60 degrees centigrade even for a few hours. The varied effects of temperature changes on emulsion parameters have been discussed before: viscosity, partitioning of emulsifiers, inversion at phase inversion temperature, and crystallization of certain lipids. In view of these problems, shelf life cannot be predicted by studying emulsions at temperatures in excess of 50 degrees centigrade even for relatively short period of time, unless there is some reason to believe that preparation will be exposed to such a high temperature in normal handling, such as in sterilization of parenteral emulsion. A particularly useful means of evaluating shelf life is cycling between two temperatures. Again, extremes should be avoided, and cycling should be conducted between 4 degree and 45 degrees centigrade. Freezing can also damage an emulsion more than heating, since the solubility of emulsifiers both in lipid and aqueous phase is more sensitive to freezing than to modest warming. In addition, formation of ice crystals develops pressure that can deform the spherical shape of emulsion droplets. Another condition for assessing emulsion shelf life is centrifugation. Stokes' law shows that creaming is a function of gravity, and an increase in gravity therefore accelerates separation. Becher indicates that centrifugation at 3750 rpm in a 10 centimeter radius centrifuge for a period of 5 hours is equivalent to the effect of gravity for about 1 year. The modest speed suggested by Becher is probably reasonable. On the other hand, ultracentrifugation at extremely high speeds, that is 25,000 rpm or more, can be expected to cause effects that are not observed during normal aging of an emulsion. Ultracentrifugation of emulsions create three layers: a top layer of coagulated oil, an intermediate layer of uncoagulated emulsion, and essentially pure aqueous layer. Rapid formation of a clear oily layer is the first clue to abnormal phenomena taking place during ultracentrifugation. It is concluded that centrifugation, if used judiciously, is an extremely useful tool for evaluating and predicting shelf life of emulsions. The third parameter under stress conditions used for assessment of emulsion shelf life includes agitation. It is a paradigm of emulsion science that the droplets in an emulsion exhibit Brownian movement. In fact, it is believed that no coalescence of droplets takes place unless droplets impinge upon each other owing to their Brownian movement. Simple mechanical agitation can contribute to the energy with which two droplets impinge upon each other. It is rarely appreciated how useful the evaluation of an emulsion by agitation at or near room temperature can be. It was already noted that excessive shaking of an emulsion or excessive homogenization may interfere with the formation of an emulsion. As a corollary, agitation can also break emulsions. A typical case well known to all is the manufacture of butter from milk. Some clear microemulsions become cloudy upon short agitation in a blender due to coalescence of particles. Similarly, conventional emulsions may deteriorate from gentle rocking on a reciprocating shaker. This is related in part to impingement of droplets and in part to reduction of viscosity of a normally thixotropic system. The need for chemical stability of the component of emulsions has already been noted. A typical problem encountered in the presence of polyethylene glycols or derivatives of polyethylene glycol is their propensity towards oxidation. This phenomenon can cause formation of undesirable odors of acidic components and of all types of oxidative byproducts. The instability of non-ionic esters leading to hydrolytic degradation may result in changes in the dielectric constant of the emulsion. This phenomenon parallels observations of physical instability and has been attributed to the formation of stearic acid form, for example, polysorbate 80. There are certain physical parameters that are also utilized for assessment of emulsion shelf life. The most useful parameters commonly measured to assess the effect of stress condition on emulsions include phase separation, viscosity, electrophoretic properties, particle size analysis, and particle count. The first parameter under consideration and discussion is phase separation. The rate and extent of phase separation after aging of an emulsion may be observed visually or by measuring the volume of separated phase. It is important to differentiate between creaming and coalescence, since the means of correcting these defects are different. Relatively little quantitative information is available concerning oil separation in practical systems in the absence of centrifugation. A particularly simple means of determining phase separation due to creaming or coalescence is apparently so trivial that it has evidently not been described in the literature. It involves withdrawing a small specimen of emulsion from the top and the bottom of the preparation after some period of storage and comparing the composition of two samples by appropriate analysis of water content, oil content, or any suitable constituent. Viscosity is an important physical parameter as far as assessment of emulsion shelf life is considered. Although the viscosity of an emulsion is an essential performance criteria, its use for shelf life studies is not concerned with the absolute values of viscosity, but with changes in viscosity during aging. The number of instruments available for the determination of consistency or viscosity is overwhelming, since emulsions are generally non-Newtonian, and since the instruments should have universal utility, it is best to avoid capillary and falling sphere viscometers. Viscometers of the cone plate type are particularly useful for emulsions, but instruments utilizing coaxial cylinders are the easiest to use. In the case of fairly viscous materials, the use of a penetrometer is often helpful in detecting changes in viscosity with age. As a rule, globules in freshly prepared water in oil emulsion flocculate quite rapidly. Consequently, the viscosity drops quickly and continues to drop for some time and then remains relatively constant. Oil and water emulsions behave quite differently. In this case, globule flocculation causes an immediate increase in viscosity. After this initial change, almost all emulsions show changes in consistency with time, which follow a linear relationship when plotted on a log-log scale. The complete absence of a slope, no change in viscosity with age, is believed to be ideal, although most acceptable systems exhibit modest increase in viscosity between 0.04 to 400 days. Other emulsions exhibit much more drastic and sudden nonlinear increase in viscosity after 2 or 3 months aging. Such behavior is frequently followed by a drop in viscosity, which is probably associated with phase separation. Another physical parameter is electrophoretic properties associated with emulsion droplets. The zeta potential of emulsions can be measured with the aid of the moving boundary method, or more quickly and directly by observing the movement of particles under the influence of electric current. The zeta potential is especially useful for assessing flocculation, since electrical charges on particles influence the rate of flocculation. If the instability is due to coalescence, the determination of the surface charge of particles may not be relevant for the prediction of shelf-life. The measurement of electrical conductivity has been claimed to be a powerful tool for the evaluation of emulsion stability shortly after preparation. The electrical conductivity of oil in water or water in oil emulsion is determined with the aid of platinum electrodes. Measurements are made on emulsion stored for short periods of time at room temperature or 37 degrees centigrade. Reportedly, conductivity depends on the degree of dispersion. Oil in water preparations with fine particles exhibit low resistance. If the resistance increases, it is a sign of oil droplet aggregation and stability. A fine emulsion of water in oil product does not conduct current until droplet coagulation, that is, instability occurs. The last parameter under discussion for assessment of emulsion shelf-life is particle size number analysis. Changes in the average particle size or of the size distribution of droplets are important parameters for evaluating emulsions. Particle size analysis may be carried out by a number of methods, each giving a somewhat different average for heterodispersed system. For example, microscopic measurement of apparent diameter given average value dependent on the number of particles of each size. Some electronic counting device measure particle volume. Coulter counter also require the emulsion to be diluted. Light scattering and related reflectance relationship have been used for particle size determination. Thus, the change of reflectance at wavelength at which colored internal phase partially absorbs the incident light has been found to be inversely proportional to a power of particle diameter. The utility of particle size for predicting or interpreting emulsion shelf-life is somewhat doubtful. Two studies utilizing fairly stable emulsions have shown that the initial increase in particle size is rather rapid, but is followed by a much slower change. Almost no change in particle size has been observed, even in case of emulsion that show appreciable coalescence due to low level of emulsifier. One would expect that particle size, the number of particles, the droplet surface area, or the droplet volume should vary linearly with time. Hill and Knight claim good correlation with experimental data by plotting the total surface area of all droplets in accordance with the following equation. Summation equals to AT plus B, where A and B are constant and T equals time. We will now discuss about practical recommendations for shelf-life predictions. A typical test program for an acceptable emulsion might establish the following points. The emulsion should be stable with no visible sign of separation for at least 60 to 90 days at 45 or 50 degrees centigrade, 5 to 6 months at 30 degrees centigrade, and 12 to 18 months at room temperature. Similarly, there should be no visible sign of separation after 1 month of storage at 4 degrees centigrade, and preferably after 2 or 3 freeze-thaw cycles between -20 and +25 degrees centigrade. An emulsion should survive at least 6 or 8 heating or cooling cycles between refrigerator temperature and 45 degrees centigrade, with storage at each temperature of no less than 48 hours. A stable emulsion should show no serious deterioration by centrifuging 2000 to 3000 rpm at room temperature. The emulsion should not be adversely affected by agitation for 24 to 48 hours on a reciprocating shaker. During the testing period just described, the samples stored at various conditions should be observed critically for separation. In addition, monitored at reasonable time intervals for various characteristics like change in electrical conductivity, change in light reflection, change in viscosity, change in particle size, and change in chemical composition. In addition to physical measurements, a shelf-life program for emulsion should include testing of the emulsion for microbiologic contamination at appropriate intervals. It should be remembered that the distribution of emulsifiers in a freshly prepared emulsion is different from distribution of one that has been aged for several months at 45 degrees centigrade. As a result, an emulsion's resistance to microbial contamination may be affected by redistribution or micellization of the preservative. From the current discussion, it can be concluded that emulsion preparation requires a blend of knowledge on excipient, formulation processes, and stability consideration. The choice of formulation process depend on the type of medicament to be incorporated and intended use of final product. The stability in terms of physical and chemical parameters to be evaluated for predicting shelf life of intended product, and on the basis of various parameters a suitable container closure should be chosen. Students are advised to consult reference literature as well as e-text attached to this module for further readings. Thank you.